Okay, so I will say a little bit more about the variational principle, which I mentioned quickly last time, and then I'm going to go to the second discretization notion of polyhedral surfaces. So I told you there is this interesting derivative form of the cosine law. I have a Euclidean triangle, length Li, Lj, and angle theta I, which are functions of the length, and then we have this formula. And so this is a really simple formula, but the first one is quite useful. You don't need to expand things out. It's also true the same form for others. So I'd like to use this to prove the first variational principle for circle packing. This is really the variational principle for circle packing proved by Duvalier, and then he uses to prove Thurston theorems. And variational principle, it turns out, is the right approach to many other things. That's why I like to emphasize. So now, again, we have a Euclidean triangle of vertices I, J, K, and the length of Li is equal to the sum of the two radii R, J, R, K. So we make a change of variable called Ui to be the log of the radius. So now this angle is a function of the log of the radius. And so the key is this formula that the derivative of theta I with respect to uj is the same as the derivative of theta j with respect to ui. And furthermore, it's a positive. So if you don't have this condition, it's true for both Euclidean, hyperbolic, and spherical. Okay, so this is all proved by Coulomb-Duvalier. For hyperbolic and Euclidean, this is a positive, and that gives you convexity. And in particular, this 3 by 3 matrix is a positive semi-definite matrix of rank 2. Okay, so one consequence is that of this is that this function f is just by integration, because the first condition simply says this differential one form is a closed one form that's equivalent to the symmetry here, and then you integrate it, and that becomes a well-defined function on R3. And this is the Hessian of this function by definition. And so negative of that is positive definite. And so it's a concave function, and that's again the definition. You just integrate it. Okay. And this is the key for producing variational principle for circle packings. And I'm going to call it, there will be several others. These are really two-dimensional Schlafly formula. And let's recall that the Schlafly formula in 3D says the following. It's a truly striking formula that if you take, say, a spherical tetrahedra, it's also true for hyperbolic and Euclidean. You need to scale a little bit. You take a spherical tetrahedra, and it has a length, Li. It has the dihedral angle, theta I. The length is really a discrete metric. Theta I is the discrete curvature. And then you have the volume. And so these are the three most important geometric quantities one can associate to the tetrahedra. And the theorem, the formula says that the volume, take the derivative of the volume with respect to theta I. And so you just change the theta I a little bit. The rest of the 5 is not changing. And the rate of change of the volume is exactly equal to half of the length at that edge. Okay. So this is exactly in this flavor. If you change this log of the radii a little bit, remains the 2, then the rate of change of this concave function is exactly equal to this angle, which is a curvature. So I'd like to show you a proof, because this is these are sort of the special flavor of argument in this discrete setting. It's always simple. The difficulty here, I mean, to Coulomb-Duvalier is that how did he find the right change of variable? And that's not easy. Okay, so and also there is a similar one for spherical one, so you need to change that as well. Okay, so So let me just quickly calculate that. Li is equal to theta uj plus theta uk. So Li partial ui is 0. It's independent. And partial Li partial uj, it's an exponential function. So it's equal to itself, which is really the radius. Okay. So that's all we have. Now let's see, what is exactly this? It turns out this quantity also has geometric meaning. So it's all of these interesting Euclidean geometry quantities come up from these formulas. So partial theta I partial uj, we use the chain rule partial theta I partial li partial uj, and then partial theta I partial lk partial uj. Well, there is one more variable which would be partial theta I partial lj. These are the three variables, but this is equal to 0. So lj equal to 0. So it's only two terms left, and these two derivatives we can use that formula, and so I'm going to write it as partial theta I partial li. That's the same thing. And this, because of the way that David Dye choose, this is equal to that. So this is e to the uj, and that by this formula, and also I'm going to take the common factor out, is cosine theta ik, and so it should be j, right? So it's j, and this is the same. So it's e to the uj. And now let's use this formula to see what is that. This is 1 over lk sine theta j. And these two are the same, right? So so let's take a look at the geometry of this of the circle packing. This is lj. This is lj. This is the radius rj. And the way to produce the three pairwise tangent circles is to just take a Euclidean triangle, draw the inscribed circle, the red one. These three intersection points are exactly the tangent point, and so these two lengths are the same. That's rj, and so so we see if I call the radius. Let's call the radius of the inscribed circle r, and we can figure out what is the length rj in terms of the radius. So so this is maybe I'm going to write this 1 minus cosine theta j. That's equal to that. It's 1 over lk sine theta j. And now I'm going to replace that by the radius. And so, so let me just make it simple. This is the radius times cotangent theta j over 2. These two are the same because of the geometry behind it. Now, now you see what do we have? We are done. So this is lk sine theta j. I have the radius of the inscribed circle, and I have now cotangent theta j over 2, 1 minus cotangent theta j. These two are the same. By simple, so the partial derivative is the radius of the inscribed circle divided by the length, which is symmetric in I and j, right? So this expression is symmetric in I and j, and it's positive, and so that's a proof of the column divided. Really elegant. Okay, now we have that, and so let me now give a proof of the substance rigidity using this really a more advanced technology. So this is So let me quickly recall that. It says that a circle packing metric, now I can think of that as a function assigning radius, right? I'm going to assign as, just say it, on a closed, it has to be compact, a triangulated surface is determined up to scaling by its curvature. And the proof is more or less 2 or 3 lines, and so that's why I like to tell you. Okay. So circle packing metric is the same as assigning every vertex a positive number. Now let's make a change according to Dividier. So I give you any function defined on the vertex. Take any real number, assign every real number to a vertex, and the radius is defined to be e to the u. In other words, radius at the vertex is e to the u of v. Okay, so this is the circle packing metric. Let's make a change of variable. In other words, I really give you a vector in R to the V, and let's produce an energy function. So the energy function is extremely simple. It's coming out of this column Dividier energy F. So maybe I'm going to write like this. Whenever you see a triangle VI, VJ, VK in your triangulation, then we assign VI, VJ, VK this scaling, right? So I just look at the function node and look at the value of the UI, UJ, UK. Whenever you see a triangle, you just put the Dividier energy to that triangle, and then you normalize a little bit. It's 2 pi minus the sum of all. This is just coming from the curvature definition. So U of V. Here by UI, I mean the value of the function as ith vertex. So in this definition. Okay, so this is now a concave function. W is now a concave function defined on a Euclidean space because it's a sum of a concave function plus a linear function. So it's a concave function. And let's take a look at its a gradient. So let's look at the derivative of W with respect to UI. So what is it? So what's going on? You look at the ith vertex, and then there will be the rest of the vertices, right? So what we are doing is I'm going to change the value of this log of the radius a little bit. I like to see what happened to this energy. Well, according to the 2D Schlafly formula in this red box, if you change this UI at a vertex, the rate of change is exactly equal to the curvature. So you focus on this triangle and you look at the rate of the change, it's equal to this angle. So this is a 2D Schlafly will tell you it's nothing but all angles at the VI, so alpha. So that's the rate of change, because if you focus on this triangle, these weights are not changing. Change that, the rate of change is exactly equal to these angles, and you sum over all angles, and that's that. And the linear term is equal to 2 pi, and that's by definition is the curvature at the vertex. So this is really the remarkable part of the calculation. So the upshot is now extremely simple. The gradient of W is equal to the curvature. The curvature is equal to the gradient of this concave function. And now the certain theorem is done, because if you have a concave function and you look at its gradient, it's essentially 1-to-1. And that's what Thurston says. So, but I should say there is a little bit caveat here. You can always do a scaling, right? This function W is not strictly concave because you can do a scaling. So it's extremely simple to check that the W is, in fact, strictly concave on the hyperplane. So so on pi, where you look at the set of all assignment where you just scale it, and so the scaling is just the sum of all vertices to be 0, and then you are done. So a strictly concave, that will tell you that the gradient of this concave function restricted on pi is now 1-to-1. And 1-to-1 is exactly what Thurston says, right? The map from the radius to the curvature is 1-to-1. That's Thurston's theorem. Okay, so that sum up so this is sort of a quick introduction to circle packing theory. I think it's really beautiful. And nowadays there are many work extending this work to allow intersecting angles and things like that. But the tangential case is really the best, and the theory is complete. For others, there are no such uniformization theorem. So now I'm going to tell you the second discretization is called the vertex scaling. Discretization of a polyhedral surfaces. So the limit of the circle packing in this setting is exactly what Yvonne mentioned it last time, that if I give you a tetrahedra, generically, you cannot produce a circle packing. So this is a 6-dimensional space, and circle packing is only 4 dimensions, so it does not apply to any polyhedral surface. And this is now going to apply to all polyhedral surfaces. So basically, the basic question is, if I give you 2 say tetrahedra, it's all determined by 6 numbers, 6 edge lengths. Can you tell me when they are discrete conformal? Because for every polyhedral surface, we know there is underlying classical conformal structure, because even at the cone point, you can define the complex chart. But that's great, where we have uniformization, but those are extremely difficult to compute. And for us, I just give you these 6 numbers. Can you produce a reasonable way to check by computer in finite time these 2 are discrete conformal, and we have some kind of a series for it? And so that's a goal. And there are several ways of doing it. And so let me maybe tell you right away. The first naive definition, it works in some context, but it took us 10 years to realize that's not enough. So let's begin with like Thurston here. In Thurston circle packing, you always need a triangulation to guide how to put the circles. The ultimate goal, on the other hand, we know triangulation is not an essential part of the structure. It's just a tool that we use to describe this prism, right? You can triangulate in this way or the other way. They all describe the same metric. So at the beginning, let's focus on triangulation. Then we're going to try to get rid of it. So here is a definition, extremely naive. This was, it turns out, first introduced by 2 physicists. They are always ahead of us. But they didn't explore this really too much. And then I was not aware of it, and so I introduced it. And I realized there's something really interesting out there. Okay, so the definition is very simple. So let's let S be, let's raise the triangulation. and I have a length metric. And so this is a be a triangulated PR surface. So every edge has a length, and I give you a function, W. So these are the discrete conformal factors. This is sort of the analog of the radii here, where the radii, you allow the radii to be changed and consider the changing within the discrete conformal class. And so we do the same thing. Say I assigned every vertex a number, and now I like to produce a new polyhedral metric and try to say this is a discrete conformal. So let's now define a new length function. I'm going to call this. Suppose you have an edge. These are all defined on the edges, right? The length is the edge function. So suppose I have an edge with endpoints U and V. I like to say what is the new length. And it's extremely naive. It's e to the WU plus WV times the original one. Okay, so this is your original length, and I put some weight on the vertices, and now I stretch the new length. And so this is length L. This is 2 times 3. E to the 2 plus 3 times L. So that's, and this immediately run into a lot of problems because the triangle inequality may not be satisfied for this. So this is a function assigned on edges of triangle. You just scale it. If you start with a triangle like this, right? So L1, L2, L3, and I put weights at the edges, and so this is W3, W2, W1, and this length after scale it is e to the W1 plus W2 times L3. And you see immediately if this weight will make it really short, right? So suppose W2, W3 are 0 and W1 is extremely negative, then this length is extremely small, and then that will violate the triangle inequality. So this is the real problem for the definition. But at any rate, define this if they satisfy triangle inequalities. We say we call these the metric a vertex scaling equivalent. So it turns out this is getting close to discrete conformal. So, but it turns out it's not the right, correct concept. Related. Okay, so that's just the definition, but I'd like to tell you why this is getting close to the discrete conformal. So there are 3 reasons that somehow justify, they make some sense of it. So the first is the variational principle, just like a dividir, and that when I see that, and so this is interesting, it may have some stuff out of here. So let me first tell you the variational principle that motivates so that at least to say this is a kind of reasonable. So the setting is really simple. Again, I'm going to just draw the picture that suppose you have L1, L2, L3. This is a Euclidean triangle, and I put these weights W2, W1, W3, W1, W2, and I scale it to a different triangle. L1 hat, 3 hat. So here Li hat is EWJ plus WK, sorry, Li. Okay, so just to scale it, assuming it still satisfies triangle inequality. And let's calculate these angles. These are the curvature condition that says, so the conclusion is this, then this matrix partial theta R partial WS plus S is a symmetric matrix. Whenever you have a symmetry, you see how to reconstruct the energy function right away. It simply says the differential form is closed and you can integrate, and is a negative semi-definite. So we can now draw the same conclusion as what Duvalier says, that so there exists a function f of w on these conformal factors, which is locally concave, such that the gradient is equal to theta. But it's only locally concave because, as we see, the triangle inequality may be violated. And even worse, for a triangle, the set of all W, which makes this scaling satisfying triangle inequality, is not even a convex domain. So this is just a pretty bad situation. But that's the first thing which says that something interesting may be hidden here. And I'd also like to tell you two more reasons that's a good thesis. This is pretty reasonable. So the second one, which is the key formula for us to prove the convergence. And so just like in Thurston's conjecture, circle packing converge to conformal, because essentially conformal is circle preserving infinitesimally. And circle packing is just a physically round circle sense to round circle. And here we have the similar situation because of this inequality. So suppose G is a Riemannian metric on a, say, on a compact surface. And then I'm going to let dg to be the Riemannian metric, the distance, Riemannian distance. So the distance between 2 points is the length of the shortest path between the two. And so for any Riemannian metric, which is defined in the tangent space, we have this the point set topology distance. And here is a formula. So for any Riemannian metric on a surface S, and for any function, you make a, we like to see what happened to the conformal change of a Riemannian metric, then the following is true. So the Riemannian distance associated to the conformal, I'm gonna just make some normalization, 4 times change of the Riemannian distance. This is a Riemannian metric scaled by a positive function. So this is a conformal change. So then for any point x and y. Okay, so let me make it more precise, sorry. So you can find a constant. So there exists a constant C, depends on the metric, the surface and U, such that for any pair of points on the surface, if you compute the distance between x and y in the conformal changed metric, and you compare that in the original distance between x and y, and we want to see how close these two are. It turns out there is a scaling factor in front of it, which is exactly this. So this is e to the u of x plus e to the u of y. This is constant c, distance to be to the third power. Okay, so for any surface here, you take 2 points x and y, and you compute the shortest distance between the two in the metric and the conformal change metric. When x and y are very close, the differences basically differ by the value of the conformal factor at the endpoints and is controlled to the third power. So this is the key for us to prove that this discretization is going to converge too. To the second power is trivial, yes. It's very simple. It's just you just say you take you prove two sides, right? You take the shortest shortest path between the two, and then you just cook up a one in this to estimate it. It's a very simple argument, but the third power is key. Yes.
You know what figure?
No, just any smooth Riemannian metric. Yeah, we don't care. But we really want to see what is the scaling factor in front of it. And the key is that this is the one that makes it. Oh, no. There are three reasons I like to say this is probably a good one. Okay, the first reason is there is a variational principle. The second one is this is probably the more interesting motivation, but it was discovered much later. So this was discovered by David Gu, myself, and Wu around 2010. And the third one is a length cross ratio. So this was really the work of Bobenko. So this is, and they really made really beautiful and important contributions here. So if you do that, it's going to preserve length cross ratio. So this L and W, it's a simple observation, but it's really essential. The same length cross ratio. So I'm just gonna just draw the pictures. These are really simple observation. So suppose I have a quadrilateral. These are Euclidean quad, and I have these lengths. I'm going to call this A, say A prime, B prime, and we defined before that the length cross ratio of this quadrilateral is A prime, B prime. Okay. Now let's do a vertex, a scaling change to this metric. I'm just going to show you two cases. It's to show. So I'm going to put a scaling factor, say lambda 1 here, lambda 2 here, and the rest is not changing. So this lambda is e to the ui. Okay, so let's just do that. Just the scale. I put a positive number as the vertices and scale it, and what you see is this new length. This will be lambda 1, lambda 2a. This is b times lambda 1, no change. There is a b prime lambda 2, no change. And now if you calculate the length cross ratio, this times that divided by this times that, lambda 1, lambda 2 canceled. So that tells you that this scaling change is preserving length cross ratio. As we observed before, a linear transformation preserving length cross ratio are exactly the conformal linear change. And so this is the reason, that, the third reason that it makes sense. I'd like to tell you a few more very simple observations based on this, which again justifies that this may well be a very good discretization. It's extremely simple. It's just a simple linear algebra. So let's take a look at the Riemann mapping in this setting. It's a classical theorem of Riemann mapping that if I give you a Euclidean triangle, say A1, A2, A3, I give you two of them. I give you any two Euclidean triangle say B1, B2, B3. Let's assume that the vertices are ordered cyclically, orientation, say, counterclockwise. And then the Riemann mapping theorem will say there is a unique conformal map. F from the triangle to another one, sending vertices to vertices. So F of AI equal to BI. So really what's going on is there is, to be more precise, there is homeomorphism from this closed triangle to this closed triangle, sending vertices to vertices, which is conformal in the interior. And the proof of this is, of course, you first send the interior of this triangle to the unit disk. And then by Karatel-Dori theorem, this Riemann mapping extends to a homeomorphism from the triangle to the closed disk. But the 3 points may be mapped into some different 3 points instead of -1, 1, 1. And now you apply a Möbius transformation to put them into the right place. So every triangle is conformal to the closed unit disk, sending the vertices to 1, -1, I, and that's this. Okay, so that's Riemann mapping. In the classical setting, the proof is very difficult, but for the discrete setting, it's trivial. So any two triangles, it's a linear algebra. So L1, L2, L3, you can always write it as it's a linear algebra. There's nothing. It's extremely simple calculation. I'm not going to tell you. So you can scale any two triangles together by this definition. And if you go to the next class, so the next class will be quadrilateral. So you have now a quadrilateral. I'm going to call this A1, A2, A3, A4. Usually we put a triangulation here to indicate you see, when you try to define this cross ratio, you always need to say which side is in the numerator and which side is in the denominator, and this diagonal tells you so. So I'm going to put that. Now the classical Riemann mapping theorem will say any quadrilateral is conformal to a rectangle. And the ratio of the side is A times A over 1 times I. That's a conformal module. So if I give you two rectangles, if they are conformally the same in a classical sense, then the length cross ratio are the same. So this is a module of the quadrilateral. Of course, we assume the map sending vertices to vertices. And in the discrete setting is again trivial that this, so maybe let me make it more precise. So any two quadrilaterals are discrete conformal if and only if they have the same length cross ratio. So two quads. Is equal to again, it's extremely simple linear algebra. So this length cross ratio should be considered as a discrete modules of that. Okay, so I think I give you some reason why this is a reasonable discretization. Now let me tell you a quite amazing theorem proved by Bobenko, Inkal, and Springborn. And the proof is essentially the same as what I just sketched. So I sketched the proof here. It's exactly the same proof. Oh, yeah. Okay. Okay, so here is a rigidity, beautiful rigidity theorem proved by Bobenkos and his collaborator. I'm going to abbreviate it as BPS. So, and the key lies in their first observation. It's a really beautiful, beautiful observation. In fact, they were able to find out what the energy function here. So the energy function is given by integration, so some one forms. And at the time I discovered that, I used Maple to find it, and Maple failed then. But now Maple can find it. It's more powerful. So the theorem says that the function f of w can be extended globally as a concave function In fact, it's given by an explicit formula, and the formula is more or less the Schlafly formula for three-dimensional hyperbolic tetrahedra. So there is, as you will see, probably not today, but tomorrow, I'll tell you what is the underlying hyperbolic geometry behind these pictures. And from that, you see immediately exactly the same proof follows. And so they prove this global rigidity theorem that for a closed triangulated surface, this is a polyhedral surface, the discrete curvature determines the metric after scaling. So if we take the scaling factor to be constant, then this is a global scaling of the metric, and so there's really nothing's changing in the curvature, and by exactly the same proof, because you have the energy functions, you have the Schlafly formula here, and the function is globally concave, and you have this. So this is sort of the rigidity theorems in the discrete. Oh, this is the same as a small f, sorry. That's why I think I'm using small f. It's this energy function over that proposition. So we only know at the beginning it's only locally defined, but you can extend it globally to the R3, and it's a concave function. And then from that, this follows. But here is the bad news is that in general, there are no existence. So if we put everything in this vertex scaling setting, it will be, the discrete uniformization problem will be, I give you this polyhedral surface. Can you find a scaling factor so that this scaled metric has constant curvature? That would be the discrete analog of it. And the answer is no. So in general, no existence result of work. There are no, there are lots of counterexamples. And so that is, okay, 5 minutes, and so maybe I'm gonna give you a preview of what exactly should be used to define discrete conformal. So again, the basic question is still the same, just like on this board. I give you simplest question. I give you two tetrahedra, and can you tell me when they are discrete conformal? And the notion is nice enough that we can establish a discrete uniformization theorem. The key lies here is the Delaunay triangulation. The key is the Delaunay triangulation. So I will say more about it tomorrow. This is nothing but the convexity in hyperbolic three-dimensional space. And so convexity is really the key to put everything into the right setting. So let me define, I should also say that I've been working with my collaborators, especially David Gu, he's a computer scientist. And to computer scientists or computational geometry, Delaunay triangulation is really the very basic bread and butter stuff. Okay, so here is a definition. Quickly recall: a triangulated PL surface is Delaunay. It's extremely simple. If for every edge in your triangulation, you take edge in your triangulation, there will be two triangles that's adjacent to it, the alpha and beta. Alpha plus beta is the most pi. Okay, and this, so that's a definition, and you can always translate this problem, this condition to geometrically. This simply says that if you take a circle of a triangle, and this is a quadrilateral in your surface, let's flatten that in a plane, and then the fourth vertex lies outside of it. And so it's a sometimes this is called empty circle condition. That D is outside of the circle. And that's exactly the convexity in hyperbolic space. So I'm going to end by, I will say more about it next time. Let me just end by saying that these triangulations always exist. So a basic theorem from computational geometry says that for any it has to be compact, closed, triangulated PL surface. Maybe I'm going to say every closed PL metric as a Delaunay triangulation. So and the proof is if this condition is violated, suppose this is violated, you have something like this, alpha and beta is bigger than pi, and then just flip it. Flip it. Changes the triangulation. And then these two angles is going to be less than pi. Let's keep doing that, and that will produce it. Okay, so I'll stop here. And the key is to start with this guy, and then you apply this process, and that's the discrete conformality where we can have some discrete uniformization.